Hi everyone, and welcome to this complete course video for the HSC Maths Advanced course. Today we're going to be focusing on function transformations as part of graphing. As part of this lesson on function transformations, we have a few lesson outcomes. So by the end of this video, you'll be able to describe what a translation is, including vertical and horizontal translations, and you'll be able to recognize where a translation exists in the equation of a graph. And then you'll be able to perform the translation of a graph. Next, you'll be able to describe what a dilation is and dilate a graph. This includes both horizontal and vertical dilations, as well as recognizing where dilations exist in the graph. Then you'll be able to describe a reflection. This includes reflections in the x and the y axis. And then you'll also be able to perform the reflection of a graph. It's super important that you understand translations, dilations, and reflections because it'll help you have a good understanding and a good knowledge base going into practical applications of graphing. We'll start by having a look at translations. Translations occur when we shift the graph around in its entirety. When you do a translation, you are moving the entire graph and every point on that graph, either up or down if it's vertical, or left or right if it's horizontal. When you're performing a translation, you're not changing the shape or the width of the graph itself, simply just moving it around. So when we're looking at translations, there's two types. The first type is vertical translations. These occur when you're moving the graph up or down in its entirety. This essentially means that every single point on the graph is moving up by whatever value of c you have. Then we have horizontal translations. This occurs when you're moving the graph in its entirety and every single point on a graph to the left or to the right by a factor of whatever your value for b is. But we'll have a little bit more of a look at C and B in a second. Now let's have a bit of a deeper dive into vertical translations. Vertical translations are essentially when you want to move your graph up or down. Like I was saying before, this means moving the entire graph up or down, not just a single or a series of points. It's every single point in your graph moving up or down. You'll see vertical translations occur in the form y equals f of x, where fx is your function, plus c. Noticing here that your c is independent of your f of x and does not occur in the set of brackets itself. In this case, c is the units that you're translating by. You're translating up if c is positive. So for example, if your value of c is plus 4, you're translating your graph up 4 units. Then you're translating down if your c is negative. So for example, if the value for c is minus 4, you're moving the graph down 4 units. We can have a look at an example here. In this graph, if we think of this dotted line as the original graph of fx and the solid line as our translated graph, we can see our value for c is going to be positive because our graph has translated upwards. Therefore, we can see here there is an upwards vertical translation. Next, we'll have a bit of a look at horizontal translations. So your horizontal translations are when you want to move your graph in its entirety, left or right. Similar to vertical translations, with a horizontal translation, you're moving every single point on a graph to the left or to the right by a factor of b. So your horizontal translations will occur in the form y equals f of x plus b. Noticing here that b has been placed inside the brackets. This is a good way to distinguish whether you're going to be translating upwards or downwards or left to right. If your value is within the set of brackets, it means you are going to be translating left or right as it's horizontal. If your value is outside your set of brackets, then you're going to be translating up or down. With b is just the units that you're translating by. It may be a little bit counterintuitive, but you're going to translate to the left if your b is positive. So you're going to be moving towards the negative values of x if your value for b is positive. And then on the converse to that, you're going to be moving to the right if your value for b is negative. This may seem counterintuitive, so it's important that you have a good grasp that to the left if b is positive and to the right if b is negative. Looking at an example, again, if we consider this dotted line to be the original value of fx, and then this solid line to be our f of x plus b, we can see we have a rightwards horizontal translation, which means our value for b would have been negative. To put these kinds of translations together, The equations in the form y equals f x plus b plus c will translate the graph both horizontally by b units and vertically by c units. When you're doing translations, it doesn't particularly matter whether you do the horizontal or the vertical translation first. The order more matters when you're doing dilations, but we'll have a bit of a look at that later. So essentially we can see when we are adding a number, if it's inside the brackets, it's going to be a horizontal translation. If it's outside the brackets, it's going to be a vertical translation. So for example, if we consider this original line here to be the first graph of fx in red, we can see we've had both a vertical translation up 3 units and a horizontal translation to the left 2 units. You'll notice here that we haven't changed anything about the shape of the graph itself. Therefore, this is just translations. The next thing we're going to have a look at is what is a dilation. A dilation occurs when you want to stretch or squeeze your graph away from or towards one of your axes. This is a little bit hard to understand, but essentially, just like we've got translations, there are 2 types of dilations, vertical and horizontal. But we'll have a bit of a deeper dive into both of these. Your vertical dilations are dilations about the x-axis by a factor of k when y equals k multiplied by fx, simply written as y equals kfx. You'll notice here that your k occurs outside the brackets. This is common, so for both vertical translations and vertical dilations, your scale factors, or what you're moving the graph by, both occur outside the sets of brackets. If you've got k greater than 1, you're going to be stretching the graph outwards by a factor of k. And then on the contrary to that, if you've got k less than 1, you're going to be squeezing the graph inwards by a factor of k. We'll have a look at this example here. Considering this dotted line as the original graph of fx, and this solid line as our graph of y equals kfx, we can see that we have vertically dilated by a scale factor of 2, stretching our graph outwards to become y equals 2fx. And this is an example of a vertical dilation. Next, we'll have a bit of a look at horizontal dilations. So your horizontal dilations are dilations about the y-axis by a factor of a when y equals f ax. Noticing here that your a occurs within the brackets. Just like how your horizontal translation, you had the b inside the brackets, with horizontal dilations, you also have a inside the brackets. If your a is greater than 1, you're going to be squeezing the graph inwards by a factor of a. On the converse, if you've got a less than 1, you're going to be stretching the graph outwards by a factor of a. So for example, looking at this graph here, considering this dotted line as our original graph of fx, and then considering this straight line as the new graph of y equals fax, we can see that y equals fx has been horizontally dilated by a scale factor of 0.5 to become y equals f 0.5. This is because when we have a factor of a that's less than 1, we're going to be stretching the graph outwards in relation to the y-axis. Putting these together, we notice equations in the form y equals k fax will have both a dilation of the graph about the x-axis by k units and about the y-axis by a units. You may see if this original graph is red here, we can see that we've had a dilation about the y-axis moving towards the y-axis. So our value for k is going to remain the same, and our value for a is the one that has changed. Next, the final thing we'll look at here is about reflections. So you can also reflect your graph in both the x-axis and the y-axis. It's best to think of this in terms of an example. So we're going to look at an example for fx equals x cubed plus 3. Our reflection in the x-axis will have the general form y equals negative fx. And you'll see here, if this red line is our original function of x cubed plus 3, this green line then is y equals negative fx. And we have reflected this entire graph in the x-axis. Then on the contrary, our reflection in the y-axis will have the form y equals f of negative x. Here, considering this red line again as our original function of fx equals x cubed plus 3, the function y equals f of negative x is a reflection about the y-axis. It's really important that you make sure you know that you're reflecting in the x-axis if you have the equation y equals negative fx, and you're reflecting in the y-axis if you've got the equation y equals f of negative x. We'll quickly have a look at the importance of the order of transformations. Doing transformations has a really important order, as you may end up with the incorrect graph if you accidentally do this wrong. Looking at the general equation y equals kf of a x plus b plus c, which includes both horizontal and both vertical dilations and translations, the first thing you're going to do is the dilation of a, being this bit here. After you've done the dilation of a, you will then do the reflection of a, which you will only ever do if a is going to be a negative number. Once you've done that, you'll then do the translation by b. Once you've done all three of these things, you can then move on to doing k. So essentially the first three things you're going to do are all going to be the numbers that are within your sets of brackets. So we go a, b. Then moving to what's on the outside of your brackets, you then do the dilation of k. Then you reflect k if you've got k being a negative number. Then you'll do the translation by c. It's really important here that you understand how to do each of these steps and you remember the order that they need to be done in order to obtain the correct graph if you're asked to perform a series of transformations. If it helps you to remember, always start with A at the beginning of the alphabet, followed by B. So we'll have a look at an example to see the importance of the order of transformations. So we'll be thinking about the example y equals negative 0.5 f of 2x minus 1 all minus 1. So first of all, we have our original graph here. This is the graph of y equals fx. The first thing we want to do here is dilate by a factor of a. So this first will squeeze to the y-axis by a factor of 2. Next, we're translating to the right by 1. You'll notice here that we don't do a reflection of a because our value for a is positive. Then we translate to the right by 1, a horizontal translation for accounting for the fact that we've got x minus 1. Next, we're doing the dilation of k, so we're squeezing towards the x-axis by 2. Then we also are going to reflect because we have a negative value here. Then we're doing the translation of c, where in this case c is minus 1, so we're translating down by 1. And that's an important example of the importance of the order of transformations. So that's it for our content for today. So we're going to have a look at a few practice questions so you can see the sorts of things you may be asked in relation to function transformations. For question 1, state two distinct transformations that will transform fx equals x squared into g of x, where g of x is equal to 4x squared. This is worth 2 marks, so here you'd get 1 mark for stating each of two distinct transformations. So the first thing we could do here, or the first method, is the scale fx by a factor of 4 to make it steeper. Essentially, you'd get gx equals 4fx, where fx is equal to x squared, so you essentially end up with 4x squared. Or the second method you could do here is to compress horizontally by a factor of 2, where you'd get f of 2x, and then once you square all that, you'd get 4x squared. So that's 2 methods that you could use to turn x squared into 4x squared. Looking at a second question now. Consider the following graph y equals f of x, noticing here that they've put on the points -1 and 11, 1 and -5, and 3 and -21 onto this graph. Whenever you get given points on a graph, that's not a coincidence, and it is something that you are going to have to use to do the transformations of whatever the question is asking you to do. So, on the same set of axes, Sketch the graph of y equals negative 2f of 2x, labeling all translated points that correspond to the points provided. For here, this is worth 2 marks. You essentially here get the first mark for doing your vertical dilation and the second mark for doing the horizontal dilation, both occurring correctly, and you'd get the 2 marks. To do this, we occur here our original graph with negative 11, 1 and negative 5, and then 3 and negative 21. Essentially what we've done here is just translated our graph, translating each of the points using the dilations that we needed. In order to do this, you have to remember that each of these points has to undergo both a vertical and a horizontal dilation. So you'll see negative 1, we've divided that by 2 to get negative 0.5. And with 11, we've multiplied that by 2 to get negative 22. The reason that this is now flipped is because we can see initially in the question, we're asked to find a negative 2 being our vertical factor. Then essentially, all you need to do is do that to both your points here. So you'll get the 1, divide that by 2, you'll get 0.5, and we're already going the other way, so we know we're going to have our point up here, and then times the negative 5 by 2 to get the 10. Then you'll do the same thing with these points here, and then always make sure to write down your equation on your new graph of negative 2f of 2x. This is a little bit of a harder question to graph if you're unsure how to change each of your points here. All you had to do here was for the points of the x, all you needed to do was divide each of those by 2 to account for the fact that you're going to have the dilation of 2x. Then for each of your y points, you're timing them by negative 2 to account for the fact that our vertical dilation is occurring to a factor of negative 2. Essentially, that's all you need to do if you're given points on a graph. Change each of the points and then essentially do a connect the dots to get the new shape of your graph. Always important to remember that if you have negative k, you are going to have a reflection. So it's important to make sure you reflect your graph as well when you're sketching it. Next, we'll have a look at question 3. So for each of the following, suggest a sequence of transformations that will transform fx to gx, with each of these being worth 1 mark, so you'd get the mark for doing the correct series of transformations. So for A, how do we transform fx equals x minus 1 squared into gx equals 3x minus 4 squared? For B, how do we transform fx equals 2e to the power of 3x minus 2 into gx equals just e to the x? Then for C, how do we transform fx equals x plus 1 cubed plus 1 into gx equals x minus 1 cubed minus 1? We'll have a look at the solutions to each. For question 1, the first thing we'd want to do is translate 3 units to the right, then we'd vertically dilate by a factor of 3. Important here to consider the order of these transformations. It's important that we first do all of our horizontal translations and dilations, then followed by the vertical dilations and translations. So when you're answering a question like this, order does matter. For the next part, to vertically dilate by a factor of 2 over e to the x, then cube root the y value of every point on the resultant graph. That's all we would need to do to translate the second equation. Then, for the third bit, the first thing you want to do is translate 2 units downwards. Then, the second thing, translate it 2 units to the right. You'll see here that the vertical bit happens first. If you're just doing translations, it doesn't matter which order that your translations occur in. So that's all we would need to do to get each of these into their resultant equations. Now finally, looking at the last question for today. The graph of the piecewise functions y equals fx is below. On the same set of axes, sketch the transformation required so that y equals 2 minus fx minus 2. This is worth 2 marks, so you essentially here get 1 mark for doing your vertical translation and reflection, and your second mark for doing the horizontal translation. First thing to consider here is that they have given you 3 points in this graph to help you sketch these accurately. You'll notice here that there is also an asymptote, and this asymptote is linked to this section of the piecewise function here, not this one here. The reason we can say this is because this part of the function here touches the asymptote, so we can say with definiteness that this is not going to have an asymptote here. In order to do this, the first thing we want to recognize is that we're going to have a reflection about the x-axis because we have a negative value here in front of our fx. So you will notice each of your pieces of the piecewise function are going to flip around. Then all you need to do is change each of your points to consider both the negative here as well as the horizontal and vertical translations. Once you've changed each of those points and considered the fact that you've got a reflection about the x-axis, all you need to do from there is join the dots. Then finally, just consider where your new asymptote is going to be. You have to remember that you also have to perform the translations of your asymptotes. If you see that your asymptotes are a vertical line, essentially all you need to do is do the horizontal translation. If you've got asymptotes that occur as horizontal lines, all you need to do is perform the vertical translation on them to get them into their new and accurate spots. So that's all for today's questions. So we'll have a bit of a review to look at what we've done in today's video on function transformations. Today, we've covered horizontal and vertical translations, how to do both of them and what both of them mean within an equation. We've had a look at horizontal and vertical dilations, including how to do both a horizontal and a vertical dilation and how to recognize where these dilations exist in an equation. We've covered reflections in the x-axis and the y-axis, as well as looking at the order of transformations. A little thing to help you remember, your translations will always occur as plus something. Your dilations occur as something times your x or times your entire function. Your horizontal dilations and horizontal translations occur within your brackets of fx, and your vertical dilations and vertical translations occur outside your brackets. It's also important to be super familiar with what it means to have a reflection about the x-axis and the y-axis. And one of the most important things to take away from this video is the order of transformations and how to do them. Particularly, this is important with the order you do your dilations, because if you mess up this order, you will end up with the incorrect graph and you will lose out on marks for that question. So it's super important that you've understood the horizontal and vertical translations, horizontal and vertical dilations, reflections, and the order of transformations, so you're able to get any marks possible in your exams for any questions on function transformations. Thank you for coming to today's video.